In this video, we will review the third and final method of hypothesis testing, which is the confidence interval approach. But before we do that, let us review the whole process of hypothesis testing. The idea behind hypothesis testing is that somebody has made a statement about the population. So they've said the average age is something, or they said the proportional amount of people who have a certain condition is something. And we don't necessarily agree with that particular topic. Next comes hypothesis testing. The first thing we want to do is to determine what our parameter is. Is this a mean problem or is it a proportion problem? So our symbol for mean is mu, and the keywords you're looking in your problem are mean, average, sample mean, sample standard deviation, S, X bar, or the question they ask is a quantitative one. What is the typical age for a student at Georgia State University? Or it could be a proportion problem where your symbol is P for your population proportion. And when you're reading these problems, you're looking for keywords such as proportion, or they give a number out of another number. So there are 23 people who smoke out of a total of 105. Percentage, they say 36% of the students agree with the current. Or the question that they asked, it gives you two mutually exclusive answers. Do you agree or do you not agree? Did you vote or did you not vote? Do you accept what they said or you don't accept what they said? Next, for the problems, you need to determine whether you have one sample or two. So one sample, you're looking at one group of individuals and you're comparing that to a mean or a proportion that's already stated. Two samples, you're looking at two groups of individuals, and you go in saying at the very beginning that the two groups are the same. So the means are the same or the proportions are the same. Next, what we need to do is to check our assumptions. So your assumptions are the items that let you know that you can use this particular process of hypothesis testing. In elementary statistics, we focus on something called parametric techniques, where the assumption is always that the shape of the distribution is approximately normal. In other statistics classes, the assumption is not made that it's normal, so they use non-parametric techniques. So if these assumptions are not in place, then we cannot proceed with our types of hypothesis testing. For all of our different methods, whether you have one sample or two, the first thing you always have to do is verify how the data was collected. It should have been collected by a simple random sample or in a randomized experiment. If you have both two samples, both of them needed to be collected by simple random sampling. Next, we need to check and make sure that the shape of our distribution is approximately normal. And we have different ways to check for this depending upon whether you have a mean problem or whether you have a proportion problem. That's why that's step number one, to make sure you know that. If you have a mean problem, one of these three things has to be true. So either in the particular problem, it states specifically that our population is approximately normal, or the central limit theorem says that if your sample size is big enough, it doesn't matter what the shape of your population is, and big enough, according to our textbook, is greater than. If you actually have the data, then you need to plot a normal probability plot and make sure that all of your points are close to that line. You don't have any points that are outside. You also want to make sure that you put out a box plot and you don't have any outliers. If you have a two sample mean problem, you just need to verify these for both distributions that you have, for males and for females, or for people over 40 and for people not over 40. If you have a proportion problem, the way you check for normality is n times p times 1 minus p. And if that value is greater than or equal to 10, then we can say the shape of our distribution is approximately normal. If you're working with the two sample proportion problem, you're using the actual proportions. So you'll do one for the first group, you'll do one for the second group, and the proportions you're using are the sample proportions. So that's the difference between these two. You must also have independence in all of your samples. Independence means that, well, part of it means that when we are doing this sampling distribution, when we're taking all of these samples, it's okay for us to have multiple individuals in different samples. So the way we say that that's okay is we make sure that our sample size is less than or equal to 5% of the population size. If you have two samples, you need to check that for both of your samples, both of your groups that you're studying. And you want to make sure that your groups are independent of each other. So if you're comparing male and females, you're only in the male group or you're only in the female group. You cannot have an overlap there. Or your age, you're either over 40 or you're not over 40. So there's no overlap in either of these groups. Once you've verified your assumptions, we need to determine what type-tailed test we have. And your keywords are what you're going to pay attention to. So less than, decreased, or smaller than means you have a left-tailed test. The symbol that you're going to use in your alternative hypothesis is less than. And when you're graphing this for the classical approach, this tells you that alpha is on your left-hand side. So your critical value is going to end up being negative. If your keywords are greater than, increased by, larger than, or more than, then you have a right tail test. That means for your alternative hypothesis, you're using a greater than sign. That means that alpha is on the right and you're going to have a positive critical value here. If you have a two-tailed test, your keywords are: is there a difference between the groups? Do the groups differ? Have the value changed? And so your symbol that you're going to be using here is not equal to. And you're going to have two critical values. You're going to have a negative z or t sub alpha over 2. You're also going to have a positive z or t sub alpha over 2. For two-tailed tests, your level of confidence is the complement of alpha. Your level of complement is the complement. 1 minus alpha gives you your level of confidence, and vice versa. 1 minus your level of confidence as a decimal, of course. So if you have the 99th percentile, this is 0.99, then that will equal to your alpha. After that, write out your null and alternative hypotheses. Your null hypothesis is always your status quo, your statement of no difference. It's already been published. It's something that hasn't changed. This is your baseline group. This is what you would think of kind of like in experimental design, your control group. So it's what you've always done, what's already been published, what's already established is no different from what you've already done in the past. H1 or HA is your alternative hypothesis. This is what you're trying to find proof of. This is what you really believe, and this is where your not equal to, your less than, or your greater than is going to come into play. What you need to remember is that here, the numbers that you have for one samples are going to stay the same. You're not going to change those. For two samples, you always go in saying your null is always that these two groups are the exact same. They're equal to each other. And I have some special notes in red for you about two sample proportions. So one note is you can write two samples two different ways. So you can leave both of the symbols on both sides, or you can move the symbol to the other side. So for here, it's just imagine if we solve this. So this is p sub 1 minus p sub 2 is not equal to 0. So it just depends on your software that you're using and how it's going to be written out. Also, another note is to be careful based upon the application of the problem. If you're talking about differences in time, then your symbols are going to be backwards. And what I mean by that, if you're comparing like 1970 to 1980, if you say the value has decreased over time, you would initially go into thinking that that decreased is less than. The problem with that is 1970, if your value has decreased over time to 1980, that really means in 1970 the value is greater. So be careful about those types of problems. Next, you decide on which type of hypothesis testing method you want to use. Your classical approach is going to always ask you about a critical value in a test statistic. This method always works no matter what kind of problem you have, left tail, right tail, or two tail. You have your p-value approach. That's always going to ask you about a p-value. This method always works as well. And the method we're talking about in this video is the confidence interval approach. It only works with two-tailed tests, so you always have to have those keywords of, are the values different? Have the values changed? Then we interpret our results after that. So we reject the null hypothesis, and the reason why we reject is because there's sufficient evidence, or we can say there's enough evidence, or we can say there's statistically significant evidence of the alternative. So you reject the null because you have enough proof of the alternative. And your mnemonic device, RS, if you reject it, is because there's sufficient evidence. Then you can fail to reject. So that means you don't get rid of the null hypothesis. And you don't get rid of the null hypothesis because you don't have enough evidence of the alternative. So your mnemonic device here, negative Nancy. You have fail and insufficient, or not and not, or fail and not. So those prefixes for in gives you a negative connotation there. Then you have classical approach, which we covered 2 videos back. You have p-value approach, which was 1 video back. And now confidence interval approach. So once again, you only can use the confidence interval approach when you have a two-tailed test. You need to create your confidence interval. If you are a graphing calculator person, then where you are going is under stat. You're going under tests. And then just like we did in chapter 9, T interval is when you have a 1 sample mean problem. 2 samp T int is when you have a 2 sample mean problem. So in our elementary statistics class, our assumption is always that we don't know what the population standard deviation is, and we use the sample values. And since we do that, we're working with the T distribution. So T interval and 2 samp T int. If we have a 1 sample proportion problem, we're going under 1 prop Z int. If we have a 2 sample proportion problem, we're going under 2 prop Z int, 1 prop Z int, and 2 prop Z int. If you're a stat crunch person, then you're under stat and T stats, 1 sample or 2. We no longer do paired in this course. Or you're under proportion stats and then 1 sample or 2. We interpret our results, and we did this in chapter 9. We say that we are blank confident, percent confident. So 95%, 99%, or 90% typically confident that the population mean, if it's a mean problem, or the population proportion, if it's a proportion problem, is between the lower bound and the upper bound, the smaller number and the bigger number. So the way we interpret this for hypothesis testing is that if the population mean or proportion from the null hypothesis is not inside of that interval, that's when we're going to reject the null hypothesis. So your null hypothesis is your baseline value, what we assume to be true. If the interval that we create based on our sample doesn't say that that number is possible, then that's when we reject the null hypothesis. 2 samples, our interpretation is we are blank percent confident, 90, 95, or 99, that the difference between the means or proportions is between the lower bound and upper bound. So for 2 samples, we're always looking at the difference. We're subtracting them. And that's why you have 2 different ways of writing your null and alternative hypothesis. And here, you're supposed to also have p sub 1 minus p sub 2 is not equal to 0 as well. So when you're subtracting 2 values that are the same, when you subtract them, you should get 0 if they're the same. An example, 5 minus 5, or 10 minus 10, or 1,000 minus 1,000, or 0.4 minus 0.4. If you go in saying that these 2 samples are the exact same, when you subtract them, you're supposed to get 0. So for two samples, the way you complete hypothesis testing is that if 0 is not in your interval, if 0 is not between your lower bound and your upper bound, that's when we're going to reject the null hypothesis. Now let's look at your completed lecture notes. Question number 1. Time magazine reported that the result of a telephone poll of 800 adult Americans, the question posed of the Americans was, should the federal tax on cigarettes be raised to pay for health care reform? Of 605 non-smokers, 351 said yes. Of the 195 smokers, 41 said yes. Is there sufficient evidence at the alpha equals 0.05 level, say, to conclude that the two populations, smokers and non-smokers, differ significantly with respect to their opinions? So for all of these problems, you need to read them and pull out the key information that you need. First key information is that you have two samples. You're looking at non-smokers and you're looking at smokers. Next, you need to make sure you know that this is a proportion problem because of the type of question that's asked. Should taxes be raised? You're either going to say yes, they should, or no, they shouldn't. So that's one way you know it's a proportion problem. You also know it's a proportion problem because you have a number out of another number. 351 said yes out of a total of 605. Then you need to always check your assumptions. When you have two samples, you need to check your assumptions for both groups. You need to check your assumption for non-smokers and making sure that your p-value you're using is your proportion, your sample proportion here. So that should be p hat. And then you need to check it for your other sample for smokers as well. And if that value is greater than or equal to 10, then the shape of your distribution is approximately normal. Your third assumption is independence. We're pretty sure that they are more than 5% of the population is bigger than 605. And same thing, 5% of the population of smokers is going to be a lot larger than 195. These groups are also independent of each other. You're either a smoker or you're not a smoker, one or the other. Number 4. Keywords to let you know what type tail test you have is that it says differ significantly. So you know you have a two-tailed test. You can write your null and alternative hypotheses two different ways. We are putting P sub n first because that's who they talked about in the problem first, non-smokers. So for two samples, whatever group is listed first, that's going to be the symbol that you use first. Our alternative hypothesis is that they differ significantly, so you can set it to 0 or you can set them to each other. Your null hypothesis is you always go in saying that these groups are the same. Now we create our confidence interval. Remember that for two-tailed tests, the level of significance and the level of confidence are complements of each other. So in this problem, they told us to use alpha equals 0.05. Since it's a two-tailed test, that means alpha is on the outsides. It's split over the outsides. So our level of confidence is 0.95. So if you're a calculator person, you're going under stat, you're going under tests, you're going under 2 prop z int, and I selected 1 and not 2. Then x sub 1 is whatever group they talked about first. First they talked about non-smokers. X sub 2 they talked about smokers. C level is our level of confidence, our complement of alpha. And when we press calculate, there is our interval. So we interpret this by saying we're 95% confident that the difference in opinions of the non-smokers and smokers is between 0.3 and 0.44. If you're a stat crunch person, you're going under stat. You're going under proportion stats. We have two samples. You have summary information because they told us 195 out of this other number, well, 41 out of 195. Sample number one is whoever they talked about in the problem first. Sample number two is whoever they talked about second. We're doing hypothesis testing, so we want that first radio button. And in StatCrunch, they do write it in this second form where you set it to 0. And this is a two-tailed test, so we want not equal to. Well, this first part, I'm sorry, is what you would do if you're doing p-value approach or classical approach. We actually want the confidence interval. And compute. And when we expand this table, lower limit is your lower bound, upper limit is your upper bound. So hypothesis testing, since 0, remember for two sample proportions we're looking for is 0 between your interval. It's not between 0.3 and 0.44. We're going to reject the null hypothesis. Our null hypothesis says that these two groups are equal. And if they're equal, when we subtract them, we're supposed to get 0. But 0 is in between 0.3 and 0.44. So we're going to reject the null hypothesis. And when we reject, that means there's sufficient evidence, or we can say there's statistically significant evidence, or we can say there is enough evidence that the proportion is different between non-smokers and smokers. We're going to skip over this example. It's a mean problem with two samples. Our approach is the same. You identify your parameter. You identify whether you have one sample or two. You check all of your assumptions, making sure that you look at how was the data selected. Is the shape of your distribution normal? Are the individual samples independent of each other? And do you have independence within each sample in relation to the population? Two-tailed problem, that's the only time that we can do confidence interval approach. You can write your answer two different ways. Calculator people, you're going under stat, test, and 2samp t-int. StatCrunch people, you're going under stat, t-stats, 2 samples with summary. Our interpretation, 95% because alpha is 5%. No, it's not always 5%. We just use it a lot though. The difference in stress levels is between 2.36 and 2.64. Here are where those values fall in the number 9. And remember, this interval is created based on your samples. This interval is created based on your samples. So based on your samples, it says the difference is somewhere over here. In order for us to say that these two groups are the same, 0 has to be in the middle of that interval. It has to be somewhere in there. And since it's not, we reject the null hypothesis. We have question number 3. This is our one sample proportion. We know it's a proportion because of that percentage. We also know it's a proportion because you have a number out of another number. It also says proportion here, so that helps. And we have one sample. We took one group of 1200. Check our assumptions. How did you select your data? Checking for normality. N times P times 1 minus P has to be greater than or equal to 0. That's our P sub 0 from our null hypothesis. So this value we're going to use with one sample is that 0.34. And then there's my note that if you had two samples, you use the sample proportion for each of your groups. When it's one sample, you use the population proportion. And we have independence. We want to make sure that our sample size is not too big. It's smaller than 5% of the population size. Keyword in the problem to let you know that this is a two-tailed test is that it says, has it changed since 2009? Null hypothesis is equal to 0.34. Alternative hypothesis, because of the keyword has changed, is not equal to. We create our confidence intervals. Calculator people, stat, test, 1 prop z int. Stat crunch people, stat, proportion stats, one sample with summary. Our confidence interval interpretation, what do these range of numbers mean? It means that we are 99% confident. Why is that 99%? Because in this problem, alpha is 0.01. And remember, for two-tailed tests, alpha is the complement of your confidence interval. We're 99% confident that the proportion of teenagers who checks while driving is between 0.26 and 0.33. For one samples, you're looking for the null hypothesis. For one sample in confidence interval approach, you're looking for the null hypothesis. Does that number fall inside of your interval? And it does not. Our interval says we think the number is between 0.26 and 0.33. Null hypothesis says it's 0.34. Since that's not inside of our interval, we reject the null hypothesis. We say that that's not possible. So there's sufficient evidence to say that the proportion has changed. And question number 4. A mileage test is conducted for a new car model, the Pizzazz. In the old model, the mean mileage was 27 miles per gallon. 30 randomly selected Pizzazzes were driven. The mean mileage for your sample, so that's X bar, is 28.6. And your sample standard deviation, that's S, is 2.2. Is there a significant difference? There's your keywords to let you know this is a two-tailed test. Use alpha equals 0.05. Mean problem, because it said mean. You have one sample. You took one group of 30. Check your assumptions. How'd you get your data? Normality, our sample size is big enough. We have 30 randomly selected Pizzazzes. And independence assumption is that our sample size is less than or equal to 5% of the population. And we're pretty sure they made more than 30 cars. Lots more. Keywords. Is there a significant difference? And that's what lets us know that this is a two-tailed test. Our null hypothesis, this is, remember, your old information. So in the old model, the mean mileage was 27 miles per gallon. We want to know if there's a significant difference. Have they made enough improvements to say there's improved gas mileage? Calculator people, stat, test, T interval when you have one sample. Stat crunch people, stat, T stats, one sample with summary. You have your confidence intervals that have been created here and here. How we interpret these values. We are 95% confident that the mean miles per gallon is between 27.78 and 29.42. And once again, this is based upon our sample of 30. So do we have enough proof to say that it's changed? Well, the mean was 27. That's what it said last in the old models. Now we're saying our mean is between 27.78 and 29.42. So since our null hypothesis value is not inside of our interval, we reject the null hypothesis. We say that the mean has changed. We have sufficient evidence. That is our review of confidence interval approach, covering chapter 10, which was on one samples, and chapter 11 on two samples. Send me an email if you have any questions.